To mám. Je to ještě jednou zbečko? Jo, toto. Že jako byla bez toho, abych já se o to nějak přičinil, tak byla vypnutá. No. Teďka, když to zkusíš. No, to je právě to. Musí být aktivní v tom. Zkusit to myš. Jo, takže já to. Jo, je to fakt jako na té relativní kvalitu, že i když budeš mířit jako na okolo.
Dobře. Takže teď už to nahrává.
Teď už se nahrává, všechno, co řekne tam, že výpověď, to chytívám. Bude to zítra ráno, to Petře, jo?
Jo, no, takhle.
Ne, myslím technika.
Jo, takhle, technika. Jo, technika bude být technika.
Děkuju. Tak jo.
Začínáme vždycky 45.
Jo, jasně.
Máme víc online účastníků než vždycky předtím.
8.
Jo. Jo, já vlastně stejně teďka, jako když jsi čtyřho, tak já neuvidím, když někdo něco bude. Prosím?
Kameru nebo vidíš tam?
Kamera funguje.
Funguje.
No, tak asi můžeme začít. Good afternoon, ladies and gentlemen. It is my pleasure to welcome here Hron. He did his master and PhD studies at the faculty, and he is employed at the Institute of Mathematics of the Charles University, and in computational fluid dynamics, in particular in fluid structure interaction, simulations of non-Newtonian flows, and also in hemodynamics, which will be also the topic of the talk. So he will today speak about numerical investigation of blood flows with slip boundary conditions. So please take the floor.
Okay. Thank you for the introduction. It's making some noises, but it's okay. So this is some a bit long-term work where we try to model some blood flows in some biomedical applications, and it's joint work with Karel Tuma and Josef Málek and PhD students Alena Jelimová, Jakub Fara, Jana Brunátová, latest Lenka Košárková. And so to give you idea, what are the situations we are looking at? So it's flowing aneurysms. So one area biofluid dynamics is applied, is the occurrence of aneurysms. So it's some pathological situation in, for example, brain vessels, where the thickness of the wall is somehow small, and some pathological behavior depending on the flow wall, that somehow you get some bulbs like this. And modern imaging methods, you very often see something like this, and there is a question whether it's dangerous or not. So you can happily have them all your life and nothing happens, but if something happens, if it ruptures, then it's very dangerous. Other situation where you might think of blood flow modeling is carotid. So that's the blood vessels supplying the blood to the head. And there are some places where very often some deposition of blood happens, and the flow gets restricted. So we might think of investigating where this happens and how it can be prevented. And the third is flow in the aorta. So it's the biggest vessel in the body going directly out of the heart. And there you might be interested in some changes in the wall, like calcification, or changes in the flow. If you, for example, the valves going out of the heart, so the flow can be influenced by this. So here is, just for illustration, some typical workflow if you want to deal with these problems. So from modern imaging methods like magnetic resonance or CT scans, you can get really full scan, for example, here of the head. And so it's some kind of voxel image where each voxel of the cube is somehow correlated to the density of the material which is there. So you might see the complete image of the head of the person who is scanned. But usually you look, or the doctors look at the cuts of the image and locate the blood vessels by some method. Like here, locate the area of interest. So looking for these aneurysms. Then you have to do some step which is called segmentation. So from these images, you want to separate the object, let's say the aneurysm where the flow happens. So this by itself is quite a large area of research, how to do the segmentation from image to the object, where you have a lot of methods like level set approaches, or lately some neural networks approaches for segmentation. So, or you can do it the old way by the natural neural network, by which I mean a skilled PhD student who will do the segmentation by hand. But once you have the segmentation, you can make your computational mesh and solve, let's say, incompressible Navier-Stokes equations on this domain with some boundary conditions. This gives you the information about the flow, and what the doctors on the other end are interested in are some indicators which can be correlated to some observations that something bad happens. So like wall shear stress is a typical indicator that something will happen. So the core, what we are dealing with is basically incompressible Navier-Stokes equations, which is supposed to be good model for the blood. So here it is for steady state, but you can imagine time derivative there. You have some constitutive flow. So for the blood, usually a part of the incompressibility, you can make some more complete, more sophisticated model for the viscosity, like shear thinning. That depends on the location. So in aorta, constant viscosity is perfectly good model, accepted. In the smaller vessels, you would consider some non-Newtonian viscosity. Then you have some boundary conditions. So inflow, typically some kind of Dirichlet inflow. On the outflow, you have something like do-nothing boundary condition, or in this case, directional do-nothing boundary condition to deal with some backflows, which happens. And then on the wall, you might have what's typically done is no slip boundary condition, but you can think of more general one, and I will tell some reasons. So the combination here is that you have still impermeable wall, so normal component of the velocity is 0, but the tangential component can range between no slip. So here you have the parameter theta, which somehow describes the character of the boundary condition. So if theta is equal to 1, you have no slip in tangential direction. If theta is less than 1, you have some kind of Navier slip boundary condition. All the way to theta equal to 0, then you have full slip on the boundary. And so why to consider this? So you have some indications. So one is there are some old experiments with blood in some apparatus where originally they measured the non-Newtonian viscosity, but they found out that in simple flows they can fit the data equally well by some Navier slip on the boundary. So there is a possibility that there is a really mechanical slip on the boundary when blood is flowing. Of course, it's hard to measure or investigate, but you can think of, so the blood itself is not a simple fluid. It's some mixture of plasma and other cells and other components. So if you would derive some kind of mixture model, then where the one component of the mixture has no slip boundary condition and the other components can slip on the boundary like blood cells, then the combined boundary condition is somewhere between no slip and slip. So there you can also end up with some kind of Navier slip boundary condition. And third observation is that, as I mentioned, the segmentation process gives you your domain, but the boundary location of the boundary is always quite imprecise. So it depends on the resolution of the imaging method. So you can think of a slip on the boundary as some compensation of the fact that you don't know exactly where the boundary is. So prescribing on this artificial boundary no slip is might be a better approximation in this case. So there are some reasons why to consider the slip boundary condition, and we try to use it and see if it has some influences in some of the cases. So actually, you have some material parameters for blood viscosity and density. You can usually measure quite nicely. The problem is that, okay, you have some boundary data in form of the inflow velocity, which is difficult to measure, and this slip coefficient, this theta or this gamma star times 1 minus theta is some kind of coefficient which is difficult to measure. So you have to guess it or do some educated guess. But let's for now think that we have problem like this. So here is a short summary of the numerical method we use. So it's based on physics fire rate tools for finite elements. So this is library which allows you to generate code for description of your problem in mathematical terms. So you actually supply your weak form in some way, and this system can translated to a finite element code generated by the library. So it works quite nicely. On the details, so if we have time-dependent problem, we use some pretty standard time discretization, like backward differentiation formula 1 or 2, or Grant-Nicholson scheme. In the space, it's standard finite elements, stable, if substable, so either Taylor Wood, or if mini element, or if we want in some cases to save the computation or use as little as possible degrees of freedom. So some stabilized P1 discretization can be used. So once you discretize it, you have a system of nonlinear algebraic equations, so some kind of Newton method. With some improvements, like that you don't have to compute the Jacobian every iteration, but you can reuse it from previous time iterations. So to speed up the calculations. And in the core, you have to solve large, sparse, non-symmetric, indefinite linear system. So for that, we use this direct method implemented in the MUMPS library. Of course, we could make it more efficient with some splitting method, but that's pretty much a little bit difficult. If you change your constitutive law or boundary conditions, then these splitting methods are quite sensitive to this. So this is like the most robust setup, which is robust with respect to changing the slit boundary condition, changing the viscosity model. It still can be nicely solved by this. So just to illustrate some problems, so there was some time ago, it's already a long time ago, some kind of challenge. So there are like 26 groups given a geometry of aneurysm with some boundary conditions in terms of, let's say, fluxes, and everyone was asked to compute the flow and get, this is velocity at some cross-section inside the aneurysm. So these answers were collected and compared, and here you can see the result. That somehow the variability of the result is quite large. So for example, you can see that some of them are agree with each other. That turns out that all these groups used some ready commercial ANSYS software, just supplying the mesh and boundary condition, and did get same results. That's nice, but compared to some other groups which use finite volumes or their own finite elements, there is quite big difference. And this is only in the velocity, so if you would compare the wall shear stress, the forces, it's even more variable. So it's like a little bit challenging to get some results which are consistent and which would be helpful to the doctors. So they don't want to see that if you compute it with one code and another code, you get different results. So that's useless. So, but after this computation, what you want to get are some what they call hemodynamic indicators, what's seen upstairs, which is typically, let's say, the wall shear stress. So the tangential force acting on the boundary of the fluid. That's a typical quantity you consider that it can have some influence on the evolution of the blood vessel. So you can define some other quantities like oscillatory shear index or oscillatory velocity index of these formulas. And they are also considered as some interesting quantities that can influence the behavior of the wall. So here, just one note. So this wall shear stress there are different ways how to compute this wall shear stress, the force on the boundary. You can either, you have your velocity field, so you can compute your stress tensor, which is derivative of the velocity field, and then compute this tangential projection. But you can also have some weak way how to compute this. So the force on the boundaries actually corresponds to some fluxes of the momentum on the boundary, so you can evaluate them in some weak sense. And that can give you some slightly, sometimes better values. And another note is that if you employ the Navier slip boundary condition, so the slip boundary condition is in fact condition that your velocity is directly proportional to wall shear stress. So you can, instead of take this, you can take your boundary velocity to be some good approximation of the wall shear stress. And that's in this publication by Jana investigated. So what you do with this information, so this was one study where we had geometry of aneurysms. And so this is the computational mesh. And this was some study where the doctors knew where the rupture of the aneurysm occurred later. So we had the location of the rupture site, and now the study was to compare the hemodynamics quantities like time average wall shear stress, which is here, or the oscillatory shear index, if there is some good correlation with the possible rupture site. So this is, for example, one case where the rupture site was a point where some jet from inflow vessel was hitting the wall, and the wall shear stress had maximum there. While this oscillatory velocity, oscillatory shear index, so that's some measure how the wall shear stress oscillates during the time, was on different spot. Another case in this study, so there were like 6, where the rupture point was located here, and it correlated with some vertical structure in the flow. So the oscillatory shear index was located at the rupture point, while the time average wall shear stress was away from this point. So this was just to demonstrate that somehow you cannot take one of these indices as a decision. And in this study, we also compared how much the Newtonian versus non-Newtonian influences the picture. So this is picture of, I think it's this oscillatory shear index, yes, or oscillatory velocity index. And its location, if you use Newtonian model versus some Carroll non-Newtonian, so viscosity depending on the shear rate. Compared if you use no slip boundary condition and partial slip, so very small slip, amount of slip on the boundary. And you can see that while going from Newtonian to non-Newtonian did not change the location too much, going from no slip to slip did change the picture reasonably significantly. So this definitely is some direction where one could explore whether this kind of slip boundary condition can make better predictions than no slip. So going a little bit in detail, how you, so if anyone try to implement the slip boundary condition, it's quite difficult how to do it. So it's easy if your wall is aligned with the with some direction of your coordinates, but in general, it depends on the normal vector or tangent vector, and you cannot easily enforce, for example, this normal velocity as a Dirichlet condition, you have to do some special treatment. And for this, we looked at the Nečas method. So somehow method how to weakly enforce Dirichlet type boundary conditions. So here is a weak formulation for the incompressible Navier-Stokes. So these are the standard forms you can get. This one is the outflow boundary condition, which is not important now. But then there are these three terms, which these three terms in the last row, which implement the Nečas method for the condition that the normal component of the velocity is 0 on the boundary. So for the Nečas method, you have some penalty term, which is here, with some weight beta, ensuring this Vn component is 0. And then you have two boundary integrals, where one looks like the force on the boundary, basically the normal component of the force acting, and something which is called sometimes the symmetry term, which makes it either symmetric or antisymmetric and consistent, the Nečas method. But there you have normal in all these terms. And if you take simple Poisson flow, so straight pipe, do this implementation, actually you can compute the analytical solution for the slip boundary condition. So it's you can have analytic solution, and here is it shown for such a mesh, depending what kind of normal you take, you get very different results. So this one, if you use analytic normal, so you know it's a cylinder, so you can write exact normal to the cylinder, and if you use it in the formulation, you get quite nice solution close to the analytical solution. But if you take the normal, this one is what we call Fawcett normal. So in each triangle, you just take the normal to the plane of the triangle on the boundary and compute it. Then you get quite bad solution with the Nečas method. And I mean, in some sense, it's clear that you are computing on piecewise planar approximation of the cylinder. So the slip condition is enforced always in the direction of the plane. So your mesh is not fine enough, you will get quite bad solution. And the last one, which is a little bit better, the normal is averaged over each vertex and then linearly interpolated on the triangles. And then this leads to a little bit better approximation. But what's clear that this is quite sensitive to the treatment of the geometry. So here are some comparison. This convergence to the analytical solution. You can have the symmetric Nečas with increasing penalty term. There is also variant non-symmetric Nečas, where you don't need this penalty term, and in this case it worked also without the penalty terms, which somehow gives a little bit more consistent results. So for the real data computations, we use this non-symmetric Nečas method for enforcing this no penetration boundary condition. So then we try to play with this slip boundary condition. So this study is studied directly to the aortic flow. So on the aorta near the heart, you have something which is called sinus of Valsalva. So it's some natural widening of the aorta. So you can imagine that here at this start there are the valves, opening and closing and letting the blood from the heart go inside. And it was somehow observed that some vertices in these sinuses are somehow important for correct function of the valves. So let us look at the flow in such a geometry. So here are a sequence of more wider and wider geometries and computed this slip boundary condition. So we can go to the next one. So the observation here was that if you have no slip, then you get a nice flow like this. It just goes straight, and then you have very small vertices in the wider valves. But if you allow slip, this goes into some periodic chaotic behavior of vortices inside the sinuses. And what's interesting, if you compute the dissipation inside the flows, so somehow one would expect the no slip boundary condition makes the largest dissipation, but in such a geometry you can end up this picture like this. So on the x-axis you have the theta, so how much it slips, where one is no slip, and more slip going to the left. And then the total dissipation goes down, but from a certain point it goes up again, and the slip solution has much larger dissipation than the no slip, which somehow is something which is observed. So these lines here are the full 3D computation. This one below is if you compute it as an axially symmetric solution. So there the axially symmetric solution is nicer, behaves like this, but the 3-dimensional computation gives you another picture. But it seems to be hard to compute, so here are the oscillations in the dissipation if you compute over time, the pulsating flow. So I think here is some picture how for the slip solution, this would be the plate again, yes. No. Yes. Okay. So there should be another video. Yes. So finally, in this test, and this is latest results, I just wanted to show because it's really fresh. Together with Karel Tuma and Jakub Farah, we have added this slip boundary condition into the frame, in the fluid structure interaction framework. So this is on the left there is a soft material for the wall, on the right there's more rigid material, and you have some pulsating flow, and you have a slip boundary condition between the fluid and the solid. So that's possible, and it's not straightforward because if you have no slip in the fluid structure interaction, you can easily incorporate this into the fact that the velocity is continuous across the interactive boundary. But here only the normal component is continuous, but the tangential component of the velocity can have some jumps. And that makes it a little bit difficult, even more difficult for the implementation. So that was for the slip and flow and interaction. As I said at the beginning, it's difficult to get this slip coefficient in some reasonable way for some measurement. It's difficult. But on the other hand, there are some, for example, 4D magnetic resonance measurements, which not only give you the picture of the domain, but they can also measure the velocities. So actually, this is a picture from this magnetic resonance of the descending aorta. So it's geometrically just a tube, but you can get some velocity information. So this would be the magnitude of the velocity inside the domain. So you can deduce some kind of information on the velocity from the imaging. It's usually with less resolution than the geometrical information, but still, if you have this data, you might think of how you can incorporate this knowledge into the computation. So again, consider the same Navier-Stokes, it's time dependent. And so you can think of what's called variational data assimilation. So for this forward problem, if you know the, let's say, the slip parameter and inflow velocity, you can compute the flow. Now you have some information about the flow, so you would like to find these parameters of your equation in a such way that the computed flow is as close as possible to the measured flow. So basically, do optimization problem with PDE as a constraint. So your Navier-Stokes as a constraint. So you have some control variables, you have some state variables, which is the velocity and pressure, and you have some model, which is this full Navier-Stokes equations. And you know the forward problem, given the parameters, you solve the velocity pressures, and you want to do inverse problem. So make your solution as close as possible to measured data and find such control parameters that this is satisfied in some sense. So your functional, which you are trying to minimize, looks like this. So it's the W represents the computed solution. So let's say velocities. In some least squares, they are as close as possible to the measured velocities you are getting from the measurement. So in order to do this, you have to somehow regularize the functional and find minimum subjected to PD constraint. So let me just sketch that it's the adjoint based optimization. So you are minimizing the functional. You actually, if you would add the constraint as a by, let's say, Lagrange multipliers to change it into an unconstrained problem, then you would set up the KKT conditions to find the solution. Here it is done by some iterative algorithm. And if you use this, what you need to compute some derivative of your functional with respect to your variables, and also derivative with respect to the control variables. And this can be done quite nicely, again, using the Phoenix 5-day Dolphin adjoint library, which actually, if you supply the forward problem, the Phoenix creates some forward code, how to compute it, but it has also possibility to derive from your forward problem the adjoint equations to solve the optimization problem and compile them again to working code. So you can do this. So let me show some example. We do that, for example, consider functional like this. So you have velocity pressure, and your control variables are the slip parameter and inflow profile. This would be the measured data velocity. So if you interpolate this measured data into your computational domain, you have some target velocity which you are trying to approximate. For the inflow, in general, it's difficult, but we can take some good approximations having the analytic solution for the Poisson flow. So it depends on the theta. If you have no slip, it's the parabolic profile, but if you go to complete slip, it's a constant profile. And you are looking to match this also at the inflow. So this matches the inflow profile, this part matches the volume velocity, and some regularization so that it's in some sense smooth. So you can imagine that this gets pretty computationally intensive. So the discretization of Navier-Stokes that we use here is this P1 with some stabilization, which gives just much smaller problems, and use some optimization algorithm. It's limited memory implementation from the CP library. And look, so this looks for theta from this range such that the computed velocity is as close as possible to the observed. So first you can think of some artificial data. So you take one of these three geometries. So for example, this one, the most difficult. Solve the Navier-Stokes. So you have some flow with some known theta. Then add some noise, make just shorter domain, and now try to fit the Navier-Stokes solution back to your original flow. So it's like artificially created data where you know which theta you use, so you know which theta you should recover or be close to. And so this is mainly work from Alena Jeronimova. So here is some comparison. So this is this artificially created data with more and more noise. And this is the recovered solution by this optimization algorithm. So we can see that it's quite insensitive to the noise, or adding quite high noise into the data. You can still recover quite nicely the solution. Of course, this is the noise was Gaussian noise, so nice noise, let's say. Usually from the MRI measurement, the noise is somehow not so nice. It can be, how to say, influenced by some other factors. But if you use this, you can recover. So the original theta was 0.5. Once the optimization algorithm stops, you are somewhere 0.47, so pretty close. So it's still to be investigated how sensitive it is to the discretization, but for now this gives quite nice results. So you can also try to run it on the real data. So this was the real data from the MRI, the velocity data. This is how it was interpolated in the computational mesh. And now, if you try to fit these data with your computation and use no slip boundary condition, you get this kind of velocity and pressure. And let's say the value of this functional. If you do this the same with the Navier slip, you get some slip parameter, which is by far away from the no slip. And it's clear if you look at the data on your computational mesh, they are not zero on the boundary. So obviously the best fit will have some slip on the boundary. And this is even one more extension that you allow this slip parameter to be variable in the space. So you can get different slip coefficient in different parts of the domain, and you get some interesting picture which can be interpreted in several ways. For example, you can think of these places where the theta is somehow different. Either your geometry is wrong there, or the quality of the blood vessel might be different. So I don't know, you could correlate probably with some, for example, calcification. So here it slips less, here it slips more. So that might be some interesting questions to investigate with this kind of results. So I see a bit faster, but I think it doesn't make such problem. So the main point of this somewhat talk was convince you that the slip boundary condition in this context is quite good idea. So almost all simulations in this business of blood aneurysm flows or other flows are done with no slip boundary conditions, but the slip boundary condition can give some additional improvement or get some ideas how to interpret the results. So, of course, it's a parameter which is impossible to measure, definitely in the real situation, but one can get some good estimate of this parameter by using some additional information, like if you know the flow field. Of course, there is a question how well you can recover the slip parameter depending on the discretization and noise in the data. That remains to be investigated. And if you get it, if it has some additional interpretations on the side of the doctors. So if you can correlate it as one of the indicators with some kind of, let's say, damage in the vessel wall. And the last point is that this fibrate or Phoenix library, together with this unjoined library, is like very nice and pleasant tool to work with, that you can do quite complicated problems, not just finite elements, but extended to the PD constraint minimization problems. And that's the context of my talk. Complete.
Thank you very much. Thank you all. So, are there any questions?
What's your relation to this finite rate dolphin thing? Is that something you develop, or is it just a toolbox to take?
It's a toolbox, but we have added some contribution to this library. So there are two students, our former students, who did take part in the development of Phoenix and Firedrake, and then contributed some parts. So it's not really a black box, but it gives you a tools that you can use to do what you need in finite elements. Yes, so it's, you still need to do some coding to use them.
Any other questions? So how big are the problems you solve? So how many unknowns?
So
approximately for these simulations?
Taylor Wood elements, it's around 1 million degrees of freedom per simulation. For the optimization, we need to use a little bit smaller problems. So this P1 stabilized gives you like 100,000 degrees of freedom on this kind of meshes.
This is for the case where the theta is one real parameter, not for the field.
Yes.
How badly does it drop if you have it variable?
Actually, not too much. So it's let's say you need twice the computational time, so it's not so bad. Yeah. From the experiments, that it's not so bad. Yeah, that was some of the experience. So the theta is quite smooth, but it's like factor 2 or maybe 3.
You mentioned three types of finite elements: the Taylor Hood, the mini element, and P1 stabilized. What is the influence of the choice of the finite elements pair? Have you did some investigation?
We did some comparison. Like there is a big difference in the computational time because of the direct solvers somewhere inside. So it scales with the number of degrees of freedom pretty badly.
Yeah, but what about the accuracy?
Accuracy, of course, there is some drop of the accuracy if you go from Taylor Hood to mini element or to this P1. You still can compensate by finer mesh. You go to the coarser elements. But for the, let's say, wall shear stress, so the forward problem, there it is of course, you get more accurate, but on a given mesh, it's reasonable, good results even with the lower order elements. We have investigated a little bit with higher order surfaces or higher order meshes, so isoparametric elements.
Yeah.
And that's quite different. There, the quadratic velocities on quadratic surface meshes are much better than the low order elements, but that's still somehow in the tests how compute that correctly. So for the optimization, where we could compare, so the results were quite close to each other.
Yeah.
So computing this Taylor Hood inside versus this P1, the final optimization theta parameter is pretty close.
Yeah.
It's much more expensive.
You showed the 26 results for this problem. Was it possible to determine which one were correct and which not, or were there some comparison with some experimental results?
Not in this case, so there was no experiment done for this, but there are some other benchmarks comparison with experiments. In this case, they were able to group the results into, as I said, this ANSYS software. Then there was the boundary condition was not given exactly, so it was given in terms of flux. So some people used parabolic profile, some people used plug flow, and that made the two distinct groups in the results. And that's basically that was the outcome of this test. There are some more recent tests of variability of these results where they focus on more specific aspects of the comparison. But yes, it's still open.
Yeah.
Field.
Yeah, I think that the results you showed were all steady state.
So this
yeah,
was steady
yeah,
state,
and,
yes. If you add,
is it not reasonable to consider in stationary
it is,
model?
but if you see the differences even in the steady state,
Yeah.
then the non-stationary might be even more
Yeah.
different. Yes, but it makes sense to do the yes, positive flow tests. So
Are there maybe some questions from the online participants?
So I have a short question, or maybe two. Can you hear me?
yeah, I can hear you.
Yeah, so thank you very much, Jaroslav, for the nice talk. So first, I would be interested to know if you would take also at the inflow a stress boundary condition, so to prescribe pressure also at the inflow. Would this whole computational framework, would it work also?
Theoretically, it could. We did some experiments with the prescribing the pressure drop, but it becomes much less stable, the computations. So somehow we don't have any really comparative tests for that, but that's definitely an option. Yes.
Okay, and from the medical doctors, what would for them be the more reasonable in conditions at the inflow and outflow? So you have chosen this directly, but is this because it's more feasible or because the doctors are more happy with this?
No, here somehow the idea why to use the Dirichlet was because we have the flow field. So in this last assimilation part, we have the velocity data. So actually we can take the measured velocity data as the inflow profile or its approximation. Actually, this assimilation, we have also variant that not just the theta parameter is optimized, but also the velocity profile is optimized, so that is close to the measured data.
Okay, thank you. And the last question, so you had this fluid structure interaction model also. So I would be, my question is, what kind of elasticity equations or model have you taken for that computation? Or what was elastic? Did you have just the interface was, or did you have?
No, full bulk elasticity, so there was visible the thickness of the wall.
Okay, so you.
Yes, Sandvenamkir of some hyperelastic material, at least for now, with some parameters not really yet directed to fit into real parameters.
Okay, so some nonlinear elasticity.
Nonlinear elasticity in this hyperelastic framework. The main focus was on the slip boundary condition on the interface.
Okay, and is this written down somewhere in this paper with Farah?
Yes.
Okay.
So in that one, there is some stationary tests and symmetric, this rotational symmetric, and we are now finishing these time-dependent tests and preparing a paper on that.
Okay, thank you.
Yeah.
So are there any other questions? So if not, then let us thank Erda once again. There is coffee here. Please.
Okay, so bye-bye.
Bye. No.